not GDG, but GDE, Google Developer Expert in ML. So we talked about Vertex AI. You know, Vertex AI is Google's platform where you can do machine learning projects. So whether you do the course or I'm sure you who has used hi Victor, who has used Vertex AI? There were some questions about Vertex AI. Oh, great to see you, Shafan. How is everything? So yeah, so this is the material for this week. As I said, we're waiting. We'll give Maddie a few minutes to join and everybody else to join. So these are the courses that you need to complete. And we do have, Victor has completed them. Victor, you're here.
Anna,
Victor,
are you sharing your screen because we cannot see it?
Oh, that's a good idea. Let me share my screen. Okay, let's go over this. Entire screen. I'll share my entire screen. So this is our tracker. Can you see the screen now?
Yes, we do.
Fantastic. So this is our tracker, which I posted the link so everybody can individually check their progress. So before I was looking at session 1, and as you see, we have quite a few learners who are, well, some still need, but this looks pretty good. I would say keep going because we are now at week 5. You are not supposed, if you are keeping on track, you should be starting on week 5 now. So if you have not completed anything, no worries. If you have completed, you are ahead. I see Paul also has completed. Congrats, Paul. How is everything? So Paul and Victor have completed. Would you like to share with everyone else what was your experience, what you liked, what you didn't like? So let's see who else. So some people have completed partially. We'll be going over. Let's see how is week 4. Week 4 had 2 badges and pretty good. Well, a lot of people are behind. So we have 3 weeks to go. Here it says session 6, but we'll have week 5. We'll have office hours, or session 5 office hours next week, and then we have our last session, office hours, and I'll have more details next week. But here are the courses that you need to complete and gain your badges. I already said save the date, October 14, because we are planning a Dev Fest. I don't have anything concrete to announce, but this is the date we've chosen. And I want the graduation to be the part of this Dev Fest. So it will be a huge thing, a big celebration, and you'll be there to receive your diploma, your voucher, to meet in person. So if you're not in New York is wonderful in October, and it's a good reason to visit New York. Here is the NLP. We plan to be at a pretty fabulous venue, which is the Classic Car Club of Manhattan. I'm sure a lot of guys, when they see that, they lose their mind, because guys love cars, and they have like a whole terrace on the Hudson River, which has cars. So this is what it looks like. And this is the venue. So it's a huge venue where you can have speakers, you can have hundreds of people, you can have food and drinks. So it's a fabulous destination. Like I said, this is our plan. It's not definitely yet, but I want to give you the heads up so that you can plan to be here. Things may change, but everybody is very much on board with this, so we want to make it happen. and to make the graduation one of the biggest things. Right now, oh yeah, so this is on Chelsea. I'm not sure the exact street, but I think it's in Chelsea Pier, so maybe it's a little bit more uptown. But yeah, definitely. Oh, so Javits Center is on 34th Street, so it's definitely all the way on the piers. It's like a big, like a warehouse, or huge space. So for those of you who came to IO Extended, that was on Pier 57, which was a little bit further down. But Chelsea Piers has all these huge spaces along the river. So this classic car club of Manhattan, I personally haven't been. So I'm looking forward to go check it out. There was a AWS summit last week, and one of the parties was there. I didn't have a chance to go, but it's a private club though, so it's not. I'm not sure if you can just go and join. To rent, you have to either rent it or be a member. So I hope you like that. Oh, Linda Wells, that. Well, Linda, we hope you come because you've been part of this course, and totally deserve to be there. I mean, not just course, you're practically NYC GDG, especially
I
when we
can't
go
wait. Thank you
virtual.
so much for the invitation.
Yeah, I mean, I'm announcing a bit prematurely, but I'm pretty sure we have a big organizing committee, lots of volunteers, so to make this happen. What else? So who wants to? Is Maddie here yet? Let's see. She said she was traveling and needed a few minutes. I don't see her yet. So who wants to say what they've been up to from Paul? I'm still banging the head on the compute vision and the ML pipelines. Oh, are you saying from last week? Wait, we do have, so if you don't count this week, we have office hours. Do we have 2 weeks? So we're supposed to have office hours next week, and then on August 17 have our final session, and we're supposed to have office hours on August 24. So technically after week 17, if you don't plan to join the office hours are to help you. They're optional. They're for you to ask questions, for you to get a chance to raise concerns. We always have great speakers who present. For example, last week we had extra content, and it's basically a chance to learn more if there are not too many questions. Mostly the questions have been about logistics, like problems. Paul has been very vocal about some problems with the labs, and I don't see many questions in the chat. I hope
There is two more questions if you scroll to the end of the chat.
oh really?
Dean.
Okay, I opened the Q&A. If you have concrete questions, please put them here so they don't get lost. So most of the questions have been about logistics. Of course, we also have the Cloud Machine Learning English channel, which is, I would say, more people are there, so better to ask there. Of course, we have our dedicated channel. We have our community. We want to keep it together for a long time, but the Cloud Machine Learning English really has people from all over, so it's a very helpful place to check if you are stuck or have anything to share. So for session 4, a couple of labs. So Liz is sharing that there are a couple of labs that cannot be checked off from the progress. Okay, let's go. Let me share my screen then and go on the tracker again. So here's the tracker. So for session 4, I see some people have completed. So Paul said he had a problem with the computer vision. Is that the problem? Oh, and Liz said there is a problem. Well, if that problem is not solved by the time we're graduating, then, and if I see some people completed it, but things change all the time. So we may say that that's off the requirements if, you know, if that's the case, if that lab has broken. So is that what you're asking, Liz, for the computer vision? Yeah, and Paul said he had a problem with that. So the computer vision. So I don't know if you know, if you, so use the check, but I love the badge tracker because if you click on the title of the course, it takes you to what you need to do. So it's easy to know what you need to do. So you're saying you cannot complete this badge. Okay. Oh yeah, I remember that. Yeah, I remember that problem that I couldn't even load one of the labs. It wouldn't at all even appear for me. So that's a known problem, that there is some lab that's not available anymore. So we'll follow up on that. What are the questions there? Are we expected? Absolutely. We are. I shared that during the office hours. So, because some people are saying we have requirements. So we are not a self-paced course. We want people, we have, as you can see, we have timelines, we have micro achievements or micro conversions, or, things to achieve every week. So to qualify for the voucher, you need to complete this by the end. I've been sharing many by the end of the course. So yes, we are going to have the graduation, but that's going to be in October. So we'll probably share the vouchers before, if you need to, if you want to get going, if you're ready. I will be the graduation, but the graduation, like I said, will be a big party to meet in person and to still celebrate as a bonus for everybody who is in New York. So if you are done on time and want your voucher, of course we make sure to provide it. As like I said, if you have been attending, I think we said, I have to double check what we said. I think we said at least half of the sessions. If you've attended the sessions and have completed this by week, session 6 is August 17th. Technically, we have office hours after session 6. So let's say August 24 is actually the end. So yes, we do have a deadline. We want people to be encouraged by others who are ahead, and that makes them think, oh, I don't want to be ahead, and to have a community. And we have speakers who support you, who answer your questions. We have Slack. So all of this is done because I actually did some research, and if you don't want to be attending, or you don't have time for this because it's an absolute time commitment, you can do self-paced courses. However, the completion rate of those is 3 to 6%. I did extensive research for multiple sources for any online tech courses that are self-paced. So this is incredibly small percentage. You need huge discipline. You don't have structure. You may have a place to ask questions, but usually you cannot contact the instructors, their, usually videos or something like that. So the reason we're doing this because we want the percentages to be much higher than that. Some of you have been part of the associate cloud engineer, and I still have to follow up, but everyone who has attempted the course, the exam, I'm sorry, not the course, the graduates who have attempted the exam have succeeded. So we have certified cloud engineers. There are some people who have still scheduled their exam. So, this thing takes a long time because, yes, we're going to graduate. That doesn't mean you immediately be going and taking the course. You may want to still take time to practice and go over more material and do more. So some people have spaced out their exam or have scheduled the exam even though we graduated last year. Some still haven't taken the exam. That being said, when you get the voucher has a deadline. So let's say the voucher expires at the end of the year or something like that. You can still schedule your exam after the voucher expires, but you need to schedule it. So you need to have a date set before the voucher expires. So once I get the vouchers, I'll know what date this is. But last year, for example, we graduated in October and the voucher expired in March. So that meant you need to schedule your exam sometime before the end of March. You could have scheduled it like in September, but if you had a deadline when you had to make that decision. So great. Maddie is here. Fantastic. Any other questions? In the learning says exam week after session week. Yes, the learning journey. So the learning journey is only for the sessions. So it doesn't include the office hours. So that's why after week 6, there is no another week. But technically, we do have another week. And the tracker only includes the sessions. It doesn't include the weeks between the sessions. But let's not waste any more time because Maddie's here. I see there's Q&A. I answered the credits. So the credits for Quick Labs are for 3 months. So depending on the first time you RSVP, if you RSVP'd at the beginning of the course, our course is 12 weeks. So you would still have another, you in total you would have 3 months. So it should be enough to complete the course. If you joined later, then it's basically 3 months since the date you RSVP. When is the exam taken? Yes, you choose the date. You can choose to take it whether if you're in New York, they have many locations in person. So you can schedule your exam, you can choose your date or time, and you go to a learning center. You can also do it online at home, but there's more. It's very strict. Like you have to be in a room with nothing around you. There's a camera, they watch all the time, so you have to, do more preparations versus showing up at a location. So Maddie's here. Maddie was asking, how is everyone? So
yeah, just gonna unmute myself. Are
I
we
can give you the floor, Maddie.
okay? Can people hear me? Okay.
Yes, we can hear you.
Okay, perfect. Okay. Yes. Okay. Right screen here. Okay. Yeah. Let me not make everyone look at your face or your own faces. So slide. I think that's what I do. I'm a little bit. This is the wrong slide, is it? Oh no, this is the right slide. I just copy my other slides. Okay, I am curious how people are feeling, right? Are there that for you that you want to uh, these things prepare for the last session, so maybe study to better help you, right? Okay, super confused. You're reading it, awesome. Which parts are you super confused about? What is the hardest for you? Wanna stop sharing? Yeah. I promise we'll get to the content, but this is a little bit important. Or maybe you can tell me later. Okay, so actually maybe go through the content then. Okay, so slideshow. Yeah, we're slideshowing. Okay, cool. So last week we did a lot of work, and we started like getting to production machine learning. We also had fun with maybe some deep learning stuff. Um, we're actually going to focus on like ML ops, right? Unfortunately, for some reason, the way it's sequenced, the labs don't have super a lot to do with what we're talking about in study session. So I think what I'll do is the slides because this is high level stuff, and then maybe do a quick summary of like natural models, and maybe talk a little bit about recommender models, just so when you're working on the lab, like not everything new is hitting you at the same time, right? So okay, so once you have a machine learning model, that's nice, but then you automate, right? You're trying to get it into production, so that going to be a lot of plumbing involved, right? Fundamentally, the job of a data scientist is to work on and the role of a research engineer or software engineer is to do the plumbing, right? So if you think of plumbing like pipelines, right? What is actually flowing through the pipeline? Well, usually data, right? And sometimes as it's going through the pipeline, there's going to be transformations and functions. So we'll talk about all of that, right? So the first half of the pipeline is getting the data to your model and then doing the training, right? And then the second is, so how do you call the model to do inference and get the results back, right? And then there's a bunch of production related issues like, okay, what if the data changed? What if the model needs to be updated? What if the model broke? So because you don't want to be doing this manually, manual processes introduce a lot of risk and also is not a good use of your time if you're an engineer. We want to set up automatic triggers so everything just happens in a continuous process. That's what CI/CD means, right? So that's kind of the high level summary of this. So let's go to the next slide. So basically what we're talking about is ML ops, and similar to DevOps, which is not a very sexy field, but it's actually incredibly important. I have not known engineers to be employed for long, and given generative machine learning, I think if you're good at ML ops, like I doubt you will be having trouble, finding work, right? The thing is, not everyone. This is a new field, so there's a lot to learn. Okay, so let's talk a little bit about what these are. Basically, making small changes and getting it to automate that process, right? So in learning, you have kind of like data validation, data processing, and getting the data cleaned up, and then getting that into the model, right? And even monitoring the model, updating the model. So continuous delivery is about, oh, I want to finish the notebook and just lob it over the wall to some poor engineer who has to wrap a API around it and make sure it's available for deployment and like prediction. The model changes are now a part of this delivery process. Because training is that when you notice something change in the data or in the model itself, or maybe it's just stale, you have new data, you have new feedback from humans, you want to retrain, right? So we don't want these things to be discrete steps. So that's kind of the whole idea of like ML ops and like a road of DevOps. So then let's talk about how we're gonna slowly click everything together, right? So usually, you think of machine learning, but actually around it, right? So the usual process of doing MR&D is that you have a process. You're gonna go and play around with all these things, and you can run some experiments. And then if something is looking like it's suitable for deployment after you did testing and validation and all of that, right? Then you're starting to think, okay, so I have something now. I want to invest a little bit more into getting this into production. So then you start to like these pieces together. A lot of companies are actually making the smart investment of setting up, ops info. They hire data scientists and like researchers. Why is that a good idea? I just told you, oh, okay, usually, you develop a model and then you clip in the rest of the pipelines, right? Well, it's exponentially difficult for this data scientists and our researchers to be productive, and they're very expensive people because it's a fairly rare talent. If they don't have the infrastructure in place, right? So it's a good idea to have engineers before we hire these people. So that what exactly do we have to essentially help us build these pipelines? Well, it's actually a library called TensorFlow Extended, right? So it's basically taking the model all the way from the model itself, extending it kind of like upstream into the data processing and storage and all that, all the way to downstream to like getting it deployed, making it available, right? So when I say downstream, that's more towards the right-hand side direction, for example, TensorFlow serving. And then when I say upstream, it's like more the data processing stuff. So you need TensorFlow data validation, right? So that's what we have available. Okay, I clicked a bit too far. I'm unable to see questions, so I'm gonna go take a quick look. Are there any questions so far? Okay, no, that's good. Okay, let's go back to this. Okay, so TensorFlow Extended. So what components are available for each stage, right? So initially you have to get the data some, right? So sometimes you don't have access to that, so you ask TensorFlow Extended to generate data for you. So that's example gen, and that has to do with like getting data. And once you have data, then there's a bunch of data quality issues, right? So for example, like what is the distribution of this data? If you have categorical variables, like which category has more, more data points, right? And also if you have continuous like variables, what is the distribution, right? Is the Gaussian? What is the mean? What is the the standard deviation and all that, right? And then after that, you can not after that, but at the same time, in the same kind of like step as data validation, generate a schema. What is the schema? This helps you produce metadata and also notice early if something has changed in your data or your model is misbehaving. Right? So a schema will be things like what type of variable this is, category are for this variable, what distribution, what should be the format. Is it like 2 floating point? Is it 8? Is it 64-bit? So those are some of the examples. And then you have example validator. So all of these are in the second step. So then the third step is like, okay, you have some data, you know what it looks like, it's fairly clean. You want to kind of convert it into the format that your model will be able to make use of, right? So once in a model that like that is equivalent to trainer step. So it's almost like you planted some vegetables, you harvested it, and now you're washing the vegetable, which is like TensorFlow data validation, that kind of stuff. And now you have to process it or cook it before you feed it to your model, right? So that's what TensorFlow transform does. So usually in machine learning pipelines, we want to use pure functions because then they're more composable and reusable. Do you understand what is the kind of like the idea of a pure function? I'm not like I'm unable to see the chat, so I'm just gonna briefly explain it, right? So a pure function basically means for any given input, it produces an output and doesn't have side effects. It typically doesn't change states, right? So that means if you have a well-designed pipeline, and you can kind of like treat these functions like blocks, right? You can maybe do one process first and then feed it into another. You can kind of like reuse it for different pipelines. So commonly in natural language processing, we have a step of like make everything lowercase, right? So whether you're processing data from Reddit for a social media kind of use case, or you're processing something from Bloomberg and there's acronyms, right? You can apply the same lowercase everything function, right? So that is a pure function that you easily put into a pipeline transformation. And then after you have all the transfers in place, then you can feed into your model. And then obviously we care about the quality of our model, and then we need to figure out how to improve it. So then that's the evaluator or evaluation. And then after you have the evaluation, you can essentially decide, okay, this is good enough or this is not good enough, and then kind of set the model to where it's being used for deployment serving, right? So that's kind of the basic idea here and the components that are available. So obviously this is a Google, product. Not only are you expected to understand like general engineering, not only are you expected to understand machine learning, you are also very much expected to understand like Google related machine learning products. So don't be surprised like there's a lot of specifics about TensorFlow extended or how Google would like you to do machine learning related DevOps on the exam. So this is just another way of showing how this pipeline can be clubbed together. So for example, you can generate some data, you can give some statistics, and then based on that, you can basically create a right. And then furthermore, as data come in, you can actually use the to basically validate, hey, is this good quality data, or is this similar to the data I was using before, right? After that, you can basically go through a translation step, and then that gets fed to your model, and then you will evaluate your model, and then figure out by either doing more data, either by doing more data pre-processing changes or making changes to your model, right? A lot of the times, making model changes actually leads to a very small improvement, and making pre-processing changes, process data actually leads to a large improvement. So we can talk a little more about that later, especially for natural language processing. And then you can have deploying to multiple places, right? TensorFlow serving is the most common, and there's also TensorFlow JS, which runs on the browser. And then there's also TensorFlow Lite, which is more targeting kind of like edge devices, things like IoT sensors or edge computing, like things like Fitbit and stuff like that. Okay, so I am going to take a look and see if there's any questions. Oops. Okay, no questions. And my apologies. This section is kind of so. Coming back to this. This is essentially like the same thing we just talked about, but presented differently. So let's talk about, right? Like I'm sure you have all seen this, remember this. So basically, you're generating kind of statistics about the data that's coming in, and basically what you're trying to do, make sure data you're continuing adding to your to your model is actually in fact what you want. You don't want to be introducing artifacts by training on data that you didn't want to train on, and furthermore, you also want to validate that there's no difference between your training data and its distributions and the schema versus what happens in production, right? So let's say you have a pre-processing step of okay, I want to make every text in the training data lowercase, and you apply that for your production data. Guess what? either your model will perform incredibly badly, or you will actually start to get errors, right? So none of those things we want. And then I actually meant to click on full screen. So this is again inferring schema. Previously we care a little bit more about the distribution. Right now we're kind of like caring about type and describe like the rules of what this data needs to be. That for defining this, which also works with a lot of APIs, is just protobuf, right? And then the validation. This is where you can look at if it's similar to what you're using the string and is as you expected. So then, this is just talking about the thing I was mentioning, which is the difference between what you're using to train your model versus what you're seeing in production, right? So this is what we call the train serving skew. So sometimes people will call your API with the right shape and right type of data, except they didn't do a processing step. If this is within your team, that's easy. You can say, okay, use this transformation pipeline, use this pure function, and then everything's fine. But for providing API for some external person to call, you can basically specify, okay, when you call, I want your data to be in this format. But it's more difficult to enforce, right? So it's better off that you say, okay, you know what, I'm going to take the raw data, as in whatever you scraped off of the internet, and I am going to provide the training pipeline, right? So they're calling with the raw data, and then your training pipeline and functions are already existing. You can ensure that at least the pre-processing is the same, and then it gives you a chance to catch if there's a the data that's causing a training serving skew. So then let's talk about this whole data transformation step, right? This is pretty key. So for this, we're going to use a TensorFlow transform. So here are some possible examples of transformation that apply to natural language processing models or sequence models. So scaling, right? Why is scaling important? Do people understand what scaling does? Anyone at all? I was asking question. Lab has coding to dos. With the deep learning exam will have MCQ, right? MCQ, a multiple choice question. So I think the exam will ask you to, but okay, how do you add your U layer to a sequence model or auto model, right? So hopefully that. Okay, so going back to the slides, do people know what any of these things mean? Like, if you're unmute yourself and speak up, because this is going to be a little bit dry, and if you don't engage, then like it's hard to stuff. So okay, after takers. All right. I'll explain this. So scaling is very important for to like optimally. We want to have ways.
Is it to normalize the data?
To have. Yes, it is to normalize that. Perfect. So, and why is that important?
So I think the values have some outliers, some may be very high values, some may be very low values. So we want to get them within a certain range, let's say 0 to 1 or something within minimum and maximum. So we want to reduce them.
Yep. So that is good. So let's take an example, right? So I'm gonna tell you, okay, like there is a new animal called a Jabberwocky, and this particular Jabberwocky has a height of 3 meters. Is this high or is this low, right? Well, if you only tell me there's one, and I have nothing to compare it against, right? So, and then what if we have another animal that's like deer, right? Well, the deer's height is you know is can you say a Jabberwocky is higher than a deer? Maybe not, because you don't know what the unit is, right? So the information trying to communicate to the model is actually where is the data, and what does this probability distribution look like, right? So generally, one helpful to keep in machine learning is imagine there's some real world process that generates data, right? We call that the data generating distribution. What machine learning learn is actually what that data generating distribution looks like. So make predictions, right? So for example, like using a very generic like human case, if your height is bigger, then you typically also have higher weight, right? Okay, so then the question becomes, okay, if we want to use your height to predict the weight, we need to understand how many standard deviation are you away from the mean, and then we also know the standard deviation and the mean of the weight. We can essentially make a similar prediction, right? Okay, so if your standard deviation is above the mean for height, you're probably also similar in terms of weight, right? So those relationships that you're asking neural network to really learn. So you're essentially making it do less work on doing stupid pre-processing and learning the distribution, right? So if you're going to be lazy as a machine learning engineer or data scientist, then you need a much heavier neural network, and it's learning from. So you might help it out a little, just like scale your variables, right? So this is actually scaling is actually incredibly important, especially for computer vision applications. There has been cases where models simply not converge just because the inputs were not scaled, especially if you're using a smaller, more compact neural network. Background runs a very natural language processing. We have this is. Okay, no guesses. All right. So, have you ever thought about how does computers read words? Basically, what happens is we're slicing the words into chunks, and we're also converting them into order, right? We have that stuff getting into later. Let's just skip that, right? Basically, this is the first step, converting like human language, like individual words or individual letters, or little sections of letters. For example, prefixes and suffixes. Yeah, into a format that a computer can read, right? Quantization or quantization, right? This is a way to basically make the model train faster and remove information that's less important, right? So if I don't particularly care about your exact salary, right? Let's say I'm making $12 per hour versus 12.1. You don't think that's a very important factor? Oh, then just say you're making less than $30 per hour or more than $30 per hour, right? This is actually a way to convert a continuous variable to a discrete variable. So now instead of $12, 12.2, you can say, are you above this or below this? And now this becomes a categorical, right? This helps to model speed, but reduce accuracy. And also, you're trying to deploy something onto a smaller device that has less compute power, and you want something to be fast. This is a common way of basically speeding that up. Future crosses, I think we mentioned this earlier. I personally haven't used this very much, but this is a way of essentially doing coding to indicate, turning a variable into a numerical representation, right? Okay, so after all of these pre-processing steps, then at the end, if you finish training your model, something you can actually apply to the model is to say, you know what, I want you to save this version of the model, right? At one point, someone asked me, what is AutoML actually doing? On the hood, a lot of AutoML algorithms will do something like this, right? You know what, I'm going to start training a bunch of models at the same time, but I'm going to choose different learning rates, right? Maybe one's starting at 0.1, another one starting at 0.5. And I'm going to see, out of all these models, when I finish training, which learning rate per test, right? And I'm going to say the model was the best learning rate along with the hyperparameter. And then so once you decided what is the best learning rate, maybe the next AutoML evolution is deciding what is the optimizer, right? So because you have a tree structure in the experiment, process the AutoML's testing, you kind of have to make sure your models are safe. So one thing you could do, you can imagine some line of code that says, okay, finish training all these models with these different learning weights, find the one that performs the best on the test set, and then save that model, right? So all of these can be done. You don't have to, wait and check if your models are done, and then go typing some code and save it as a file, and then email your buddy and be like, hey, this is the model. If you want to serve, you have to change your file path. All of these things can be did. Okay, so train serving skew, I think we probably talked about this enough. So I will, if there are questions about this, let me know. But what this is actually that the processing steps for whether you're doing a batch prediction or if you're doing a real-time prediction, whether you're training, whether you're doing serving, to be the same steps, right? So you have the same so it's saying that processing function is implemented in TensorFlow transform. This is the modeling stuff we kind of have focused on in the first part of the course, but this is actually the less important part, right? Right now, enough people can figure out how to, call API or tweak a BERT model or even like a GPT model to make it work better for you, even fine tuning. But what actually makes company win and gives them like a huge competitive advantage, and also indirectly you as an engineer, what makes you win in the market and what gives you a competitive advantage, that is actually the first half, right? All the DevOps stuff, the ML ops stuff, and that's also not a pretty large part of the exam. Okay, so let's just talk about this very quickly in terms of like the components that are available and what you can use for different chunks, right? So training, read the data, right? And then the pipeline that you feed it through to do pre-processing, and then you can start basically working on your model. Now, what TensorFlow Hub does is that it has it's a repository of reusable processing functions and also model components, right? So enough image classification cases, and someone wrote a very nice chunk of code that converts a cipher image into a numerical representation that's ready for kind of a computer vision model or computer vision task. So, for example, you use the same processing function on a cipher dataset or like image dataset, such that your model learns to detect and give you the coordinates where like is in that photo, or also classifies if this model has a copy in it, right? So that's what that first part is showing. And then after that, you can basically code your model using like domain estimators, or you can start a model using Keras, right? So TensorFlow has a higher level Keras API where it's simple for you to specify models. All you have to do is pass in the arguments. The most difficult part I found with working with TensorFlow is understanding like the dimensions of the layers. But if you use Keras, a lot of it is automatically taken care of. And if your model is misbehaving and or giving you errors, one of the most common ways that happens is you didn't specify the dimensions correctly, right? So that's one thing you have to watch out for, and you more experience as you do more of these things. And so you have your model, you have your data now. You're like, okay, do some grading, like we talked about last time. So then you have distribution strategy. You can train on you can train on GPU, train on TB, and we also talked a little bit about how the different strategies would affect whether you convert faster, whether you're more heavy, whether you're going to be spending a lot of time sending data back and forth, right? So that's another choice you have to make. So at the end of this, you train your model, save it now. So then here are your options. One, serving is basically cloud, right? Or you can actually package it so that they can serve it on-prem. A lot of companies sensitive data, governments, they have like specifications. They're still like a little more old. Also, they request that not using cloud services and to serve the model on-prem. So that would be TensorFlow serving, TensorFlow Lite. This is for kind of like edge devices, IoT sensors, kind of thing. Also fairly productive for setting like federated alert. browsing the browser and works on Notebook. That's pretty cool. For people who are mostly learning machine learning for products or trying to start a company, TensorFlow.js is a really sweet way of doing that. And then you can also wrap another API around it, no matter what is like the language of your choice. So that's kind of another way that Google wants to understand the variety of solutions that are available. So after this large, sales pitch and advertising of Google, available components, let's go through some simple questions. So this question I will just let you read because I'm at a reading, and then we will do some voting in the chat. So I wanna see actual votes.
That's not nice.
And I will. Yep, people have some questions. Okay, so go back to. I mean, like enough people have.
Are you waiting on an answer?
Yep, waiting on answer. There's an A. That's awesome.
A is the right
Any other
answer.
answers? Okay. Do you want to explain? Oh, I don't know who spoke up, but did you explain why A is the right answer? I'm guessing no. There's only okay. Okay. But I have objective. So I want to say you're not super sure they like how can you kind of like pick up signals so no to answer A, right?
Creating two
Get
folders
closer to the
would be tedious, right? So option D couldn't be. Like in option D, it says to manually place images in each folder, and the question says there is a large repository, so it would be tedious.
Yep, exactly. So even know any of these, you're like, man, okay, that's not a terrible idea. Immediately is okay. So out of it, what is the here? So you have to tag identify logo and use it as a label, and then transition on your. Oh, if you already API that your logo, why do you need to train? Kind of, but that is kind of reading this question. So let's see if we are correct. Yeah, we are. Awesome. We're doing so good. Everyone's gonna pass. Okay. What do we see? You have to understand how trade-offs. A key question. Of like, machine learning, especially if you're on engineering, and also on this exam. So votes. Yes, Paul. Absolutely. And service is available. Your mileage may vary, so try a few different. Yeah. Do we have any answers for this question?
B.
Agree. We got a couple of these. Awesome. Anybody else? No one's contrary. No one wants to be brave. Okay. Okay. So answer A. And let's figure out. Right. Do you want the answer correctly in the ranking? C and D not correct. Like E, that's not correct.
Batch prediction would not be sufficient for this low latency serving.
Yes, that exactly. Okay. So suggest the C, and that is like the C you want to watch out for. It's So let's talk about the difference between batch prediction versus batch prediction. You have, like a bundle of data points. Ask model to process all of them and then give you all the results back, right? But if I'm playing this game and I want to predict, I only care about my. I don't care about that I'm playing a game. In fact, already this whatever. Right? So C and D the outcome. So then, what about what about the next two? Right? Do we want or GPU? How do you figure that out?
Well, for A, it says the TPU is to optimize model training speed, but they seem like they're more concerned about the inference at serving time than training.
Perfect. Exactly. That's a true question, and you didn't take my bait, so that's awesome. Exactly. So this does not care about training, right? It's not like learning. It's not doing learning per se. So serving speed. So A is also not the right answer. So that's, a lot of times the multiple choice we the right answer. Usually, so we have more left. What would people be most interested in, right? I know the labs are like natural processing based, sequential model based. There's also one that's recommendation. I can give you like a quick summary about any of these topics. So it's just a matter of like which one is more useful to you, and if you want me to go through that or not. I can kind of like give you a quick crash course without slides because I don't have slides prepared for this. Similar to what we did for the deep learning stuff. So I need to see votes. What do people want to hear more about? There's one vote for NLP. That's not a lot of votes. 2 votes. Okay, 3. We have 40 people. I need to see more data. Okay, all right. So I think it's just NLP skewed. So sorry, William. We can talk about recommenders afterwards. But let's talk about NLP, right? Okay, cool. So what is the level of most people on this call who wants to hear about NLP? Like, up to what concept is familiar to you? Do people know what a transformer is? Thumbs down. Yes, I would make that inference as well. People care about NLP because of BARD. So do we know what a transformer is? Thumbs up, thumbs down. I'm trying to figure out what is the right level to start this conversation at, right? I don't want to be like, this is a word and this is a letter. So anyone familiar with transformers? Okay, good. Anybody else? If you're not familiar with transformers, then thumbs down, right? I'm trying to like slowly trying to like back off until we understand like what level we need to start with, and I'm not seeing a lot of data. So you guys know what a transformer is? Okay, so okay, it may be worthwhile to take this. Okay, what does the test focus on? It's a good question. So it doesn't necessarily like focus on the architectures, but you will need to know how to do that for the labs. So which is why like I'm trying to figure out like how to best help you, right? I don't want to get people to get like super stumped. So okay, this whole thing started with like how do we represent text, right? So you can't really necessarily feed words into a neural network because neural network operates on numbers, right? So the quick way of doing that is essentially doing one-hot encoding. So do you remember one-hot encoding is? I'm gonna assume yes, right? So then let's figure out how do you do that for a language, right? So how many words do we have in English? How many words do we have? Like at least a couple thousand, right? So that makes one-hot encoding very difficult because one-hot encoding for however many types of the same you have in that general category. For example, pets, right? Let's just say there's cats and dogs. That's the dimension of your encoding. So if you want to represent 1,000 words, then you have to have like a 1,000-word vector. So that's really like large, right? And this is one of the reasons why it takes so long to train. So then we a way to represent words into a more compact dimension, right? So that's what some of the earlier models did. So basically everything around like word to vec is around that, right? And then people figured out, okay, so once we have that, we can actually use a neural network to learn the representation. That's called embedding, right? So instead of doing one hot, we're going to feed the encoded like 1,000-word dimension vector into the neural network, and then we're gonna compress it. So the output is actually a smaller vector, right? So once you have a smaller vector, and this is what we call a representation, either it represents a word or represents a sentence or sometimes even represents a paragraph, then you can do computations based on the representations that are now vectors. So far so good. We went from like how do we turn text into something that neural networks can use. That's called encoding, like one-hot encoding, into how do we make it more useful by reducing the dimensions. That's called embedding. So once you have embedding, basically what you have is is essentially a feed-forward neural network, right? So the other key thing that becomes very important for language is the order of things, right? A milk cow is not cow milk. So a milk cow is fundamentally a animal. Cow milk is more like a liquid. Right? So order matters. So then how do we handle order? That's when recurrent neural network comes in, right? So basically it's viewing the words like by going through it in a sequence. So first off, you're taking chunks of word, maybe 3 words at a time, right? So I have a dog and a cat. So you start with I, and then I have, and then I have a dog, and then start to slide, right? Why important is because words that occur in a similar context tend to have similar meanings, right? So in the sentence, like I have a dog and a cat, while cat and dogs are more likely to co-occur in a sentence because they're both in the category of pets. It's more rare to hear someone say, I have a dog and also a tiger, because tiger is not typically pets, right? So that is the common hypothesis of like why context matters. So then the way you actually learn how to represent a word is basically give the model the surrounding words and make it predict the word in the middle, right? So or you can give it the word in the middle and make it predict the words on the side, right? So if I give you the word cat, you're like, oh, maybe the word dog is rounded somewhere, right? So that's how you learn like a better representation. And then what became apparent is essentially transformer, right? So there's a very famous paper called Attention is All You Need. So what attention does is that not only does it allow you to account for sequence, it also gives you the idea of like how far back do you need to go to understand which words are important, right? So let's just say I have a sentence like I have a friend, his name is Fred. So the word his refers to both the entity friend and Fred, right? So how does the computer learn to understand like, oh, this is referring to these two things? That's what essentially LSTM does, and also like what LSTM is like starting to do, but attention fundamentally fixed, right? So transformer models are essentially a supercharged version of attention. So before you move into the fancy large language models, I recommend you spend some time understanding like LSTMs and also the attention mechanism, because in a large language model like a BERT or ChatGPT and vice versa, there's a lot of like attention mechanisms everywhere, right? So basically, let's use a translation example. You have a sentence you want to translate into French. I have a cat. I don't know what the French is, but there's a French equivalent. So what transformer models do is that not only do you pay attention to the relationship in your embedding layers, you also pay attention to what you need to consider when you do the translation, because different languages have different structures, right? So for example, in English, using the cow milk versus milk cow example, the more important word is always at the end. The front half is more like descriptions of the last word, right? In some other languages, that's different. In some other languages, the order in which you write the language is different. In some other languages, it's not even character based, right? It's not letter based. It's more character based. So it goes from understanding what it needs to pay attention while it creates the embedding into what it needs to pay attention to of the input, but also how you decode it into the final translated version, right? So the other thing people will come and tell you about is the encoder-decoder model, and that is commonly associated with transformers, because encoder is basically how you embed the input text, right? And then let's say the task is translation. You first have to embed whatever source language into a representation by going through the embedding layer. The first step is what we call a encoder model, right? So usually it starts with a very large, or like a very long vector, and slowly produces a shorter vector, right? And then the decoder layer is kind of like, okay, so you tell me what this looks like from English. I'm gonna take the English version, the English embeddings, and I'm gonna try to blow it up and transform it into like a French output, right? So decoders typically have the structure of like having less like lower dimensional input layers and higher dimensional output layers, because once again, what is the output? It is another one hot encoded vector which has a large dimension that tells you which French word it is, right? So that's kind of the general architecture of these large language models. So I just went on for like quite a bit. That kind of like takes you all the way from the like very early stages, about like more than 6 years ago, to currently. Are there specifics that people like really want to double click on or drill deeper into? So I'm not seeing a lot of responses, and if people just want to like have some time to work on the labs, that's totally okay too. Thumbs up, thumbs down. Questions in general. So someone's asking me, does exams have lab examples or lab case studies? Based on what I know, no, but you will get asked questions like, oh, you're trying to do real-time prediction for an online multiplayer game that has a lot of possibilities. Which one do you choose, right? So unless you know how to do the labs, you will have a very hard time of like making correct decisions on these questions, right? So and furthermore, no one's gonna hire you just because you have a certification. Like you will maybe get interviewed sooner. So if you don't know how to do the labs, it's in the end not productive, right? Yes, Chevron, thank you for your kind words, but in the end, we do need to do the labs, so that's like a little bit unfortunate. So I actually went through all the labs, double checked everything like kind of works. The only problem is I have to warn you, a lot of these labs take a long time to run, right? Especially the ones in the the natural language processing section. So the good news is, even after your lab has ended, you can still look at your notebook, right? So I highly encourage you to dig through the notebooks and look at the details. In the end, like when you actually get on a job, the devil's always in the details, right? You can just specify like one input and your model just simply won't learn. So the details are super important. Don't be overwhelmed by all the parameters and all the different layers. Just trying to understand like what is it trying to do, right? So yeah. Are there any other questions? Are there any other questions that topics? Oh yeah, recommender systems. Okay, so I can briefly describe that. I happen to spend a lot of recommender models, so will be good. I'm gonna read what I'm saying. It's not example of pre-processing. I'm not super sure what you mean by that, but we can like take it offline. Okay, recommender models. So the way we typically interact with recommender models is in some kind of feed, right? Your Facebook feed or your Instagram feed. So what these models are trying to do is basically saying matching some kind of demand with some kind of supply, right? So concretely, let's take the example of Netflix, right? Netflix is actually probably one of the leaders in recommender model because that's their entire business, right? But when you really think about it, so is every social media network, so is every e-commerce platform, right? So recommender models are very important, and unfortunately, these models have been in our lives without anyone noticing for a very long time. So going back to Netflix, you have demand, and let's just call these users, right? And you have supply and or products you're trying to match with the demand. So in Netflix example, this would be like videos that you can consume, right? So then the question is, what is success in this case? What is an indication of a successful match? Maybe it's the user actually watching a video for a long time, and this is the YouTube algorithm, right? Like which videos they recommend. Well, if the users watch all the way to the end, right? And for Netflix, maybe it's a score. Does the user give you a score of 5 out of 5 or 1 out of 5? Do they click on it? Do they not? Right? So what the objective is of a recommender system is that it's optimizing for that metric, right? And notice how immediately we have a problem. The metric not necessarily measure what is successful for the business, right? So maybe Netflix's like ultimate objective is to like improve user happiness, or maybe Google's objective is I want to match people with the information they need, right? How exactly do you measure that? Do you like go ask every user? You can't. So you have to use some kind of like proxy metric, which is usually a click rate, right? Awesome. So now what is operating on? You have a bunch of users, you have a bunch of products. It's trying to optimize a metric, maybe the click rate, right? So if I say, hey, user, look at this, does the user click on it or not? Let's just say that's the common problem setup. Then what are we doing exactly, right? It's actually under the hood learning exactly the same thing that a NLP model is learning, because it's also learning an embedding, right? What is an embedding again? It is a representation of your product and your user, right? So in a recommender system, there's typically a bunch of embeddings that represents what the users are like, and a bunch of embeddings that represents what the products are like, right? So now once we get to the point of embeddings, there's a key thing we have to talk about, which is similarity, right? So when you go onto Amazon, and this is another classic example of like a recommender system, you will typically see something like, oh, other users like you also purchase these items, right? So what do they mean when they say other users like you, right? So they're actually comparing the vector in their machine learning system or represents you as a user versus another vector that maybe represents me as a user, right? So then we have to understand like what is this idea of similarity. Similarity and distance is kind of the same thing. It's basically a measurement to say whether it's a distribution or you're comparing the individual digits in a vector, how close they are, right? Usually, more similar items have similar properties. So, for example, there is a very famous example of like natural language processing where they did, king to man is queen to woman. So you understood that there's like genders along some dimension. So you would expect king and queen to be similar to to be each other if there's a dimension called like what is your social status, and then you would expect man and woman to be far away from each other as words along the dimension of gender, right? But be closer to each other along the dimension of like social status compared to man versus king. So all that said, you're basically using a neural network to learn how to represent what a user is like versus what a product is like. And then once you have these embeddings where you're using that to do is say, okay, so given Maddie as a user, this is her embedding. Can I look through all the vectors in my pile of users to find, oh, like which users are closest to Maddie? Okay, I found a bunch of users, maybe like one's Krista, maybe one's William, maybe one's Vulcan. And then it's going to ask the question, okay, so if these are the users most similar to Maddie, what other products did Vulcan and William or Anna also purchase or consume, right? And then maybe we should recommend those to Maddie too, right? And then another way of doing this is that, okay, so we went from Maddie as a user to people who are similar to Maddie in these representation or vector space, and then we went from there to the product space, right? This is a list of products. Can we also ask the question, not only are we going to represent the products that these people already bought, but also what products are similar to the things that are already bought that we should also recommend to like Maddie and Anna and Vulcan and William, right? So that's basically what's happening under the hood of a recommender system. So yeah, that's kind of like the quick summary. Do we have any more questions about that? So there's a couple minutes left, so I want to maybe share my screen and show other what this looks like in real life, right? So I'm going to show you a notebook. Okay, so I have some sentences here, right? So this is a sentence, and I want you to pay attention to. This is a very famous example in natural language processing. Is that there's many uses of the word, right? So in the first instance, this is a natural institution, right? In the second instance of the in the last to like physical the landscape, something like geospatial, right? So can we train a language model and make it such that it understands, even though this word bank is the same in all three cases, they're actually different than each other, such that when we calculate a similarity of this bank as a word versus this bank as a word, due to the fact that the surrounding context is different, for example, bank vault versus like bank robber, could it learn that, okay, like the if a word bank near the word doesn't mean it's the same word bank that near the word vault or robber, right? I have the example, which is the word sink. So rail sinks. These are just like very demonstrative concrete examples, just to show you like what actually happens here. It actually works, right? So this sink is a verb, right? The kitchen sink is a noun, and then the last one is also a verb, right? Okay, so let's look at after we train this model, what it's able to do. So here is basically the numerical representation of that word, right? Like I said, if you're going to like do encoding, you get one hot encoding, there's going to be a large number. So sync here will be space, and you can see number as high, right? So this is why when you're doing natural language processing, usually you limit your vocabulary. You're only going to focus on the not the most frequent, but the most like common but important words, right? Most we don't want words, we don't want the word elk, for example, because it just doesn't show up very often. Larger output and input space is, right? Well, the word a, like a cat, shows that word has zero meaning, right? So you're really trying to limit your vocab to the words that are coming up frequently enough that has the most meaning, right? So I'm just gonna skip all the way to the end because I don't want to like take up too much time here. All that is to say, after a lot of work, here is the here's kind of the interesting outcome, right? So I am calculating cosine of the words in a sentence, right? So some this is basically trying to calculate, does it understand that these two banks mean the same thing, and then these banks are different, versus like the way different we're using the word sink, and here, right? So while I'm using the vault bank versus the robber bank, notice these are the word bank that shows up in our context, right? Similarity score is very high. You can see that, right? Now, if I compare the word, the embedding of the word that's near the word vault versus the one that's near river, the context is now different. Even though we're getting the same word, the vector is actually different, and therefore similarity score is low. So okay, so that's a famous example. Maybe you did some like custom tuning. Let's for example, the word sync. So comparing the embedding for sync, one for morale sync, both sync. Once again, it's only the word sync. It doesn't include the word morale, right? Okay, so between the two words sync in similar, because they're both verbs. The similarity score is like decently high. But what's more important is that it's much higher than when you compare the word sync, which is a noun, versus the verb sync, and vice versa, right? So basically, this is a way that this works. So in this little bit, I want to briefly summarize what we just talked about, right? So these large neural networks does the thing called embedding. What is an embedding really? It turns something in the world and learns a numerical representation, right? So then once you have a numerical representation, you want to make sure this representation is good, right? So what does good mean? It means that you can use it to do things like similarity and have it match in the real world, right? So put the whole real world and fed to a neural network, I want to be able to say, is New York close to Syracuse? It should be closer than New York versus Vancouver, right? So those are the things you can test. So okay, so you go from something in the real world, data in the real world, you get a numerical representation, and then you're doing similarities, right? So similarity, which is an example of like word being similar. And we also talked about how we can use similarity between an embedding of a human, a user, versus embedding of a product to do recommendations. So that's kind of like the quick summary of like using large language models for both sequence and recommendations. Are we good? Any questions about that stuff so far? Someone's asking for the link to the collab. I can share that, but this is just like my own like kind of a notebook. It will take me some time to like clean it up. So give me some time, and when it's done, I'll like into the general channel. How about that? Any other questions? Like a little bit useful for folks? Okay, so H. Thompson is a curveball here, and wants to know how, or I assume it's he. I don't know. Wants to know what these transforms are in the context of a recommender system. So I will do that. Okay, so scale 2. Okay, so let's say I'm recommending news articles to a user, right? Scale 2. How long does this user spend on each news article, right? That's something we can scale. Let's say I personally have a fish tank, and I don't have a lot of time to read stuff unless it's like a research paper. So maybe when I'm looking at social media, I spend 2 seconds, if not less. Someone else who's a like a novelist or has a like more attention span actually enjoys reading novels, so they spend more time reading like online long form novels, right? So then in that case, we can actually do a scale, right? Out of this distribution of everyone that's reading stuff online, what's the mean time that people spend on article versus what's like the standard deviation, right? Maybe Maddie has like ultra short attention span, and therefore I spend way less time. and then it's more likely that you'll recommend shorter things to me or social media profiles, social media posts to me, versus someone who's like spending a lot of time reading like long form novels on the internet or fan fiction. Then you may recommend longer articles or anime series to them, right? So that's of a scale. Bag of words. Okay, so if you're looking at bag of words, that's typically like a natural language setting, right? So bag of words is actually not super common anymore because, like I said, when you say the order in which you put things into the bag, right? So if I have a bag and I'm putting marbles in it, I don't care if I put in the red marble. Let's say there's only one red marble and 5 blue marbles. You don't really care once it's in the bag, and you can't even know did I put in the red marble first or in as the fourth marble, right? So that kind of destroyed the sequencing. But you can actually say, let's look at the title of an article, right? In this bag of word, is there the word transformer, right? So if there's the word transformer in this bag of words in the title, then go to someone who's doing natural language research, right? So those would be some like very rough examples of how these would be used. Now, this is a good one. Let's just say Netflix has some idea of or actually, let's go back to the example of like recommending things for people to read, right? If you happen to know my salary data, or if you happen to know maybe like my longitude and latitude, right? The fact that I'm like on the north side of NYC versus in the middle of NYC versus a little bit south of NYC, it actually doesn't matter. You just want to have a bucket of saying, okay, from this longitude to this latitude, this is the top boundary and the lower boundary of New York, right? Inside is considered a New Yorker. I should recommend them, the New York Times. Everything else doesn't matter, right? So that's the example of bucketization. Can you imagine how terrible it is if you had to? Oh, I don't know what's happening because I think Siri is acting up now. So.
Examples of how do you transform? Check.
Okay. Siri, but that's fine. But can you imagine like if you had to do like individual predictions for every 2 steps you move in your right? That would be like pretty difficult. Okay, so hopefully that's kind of helpful for understanding recommenders and how these pre-processing steps are applied. Last question. One is asking, how do you avoid radicalizing people by constantly recommending Bin Laden speeches? Okay. This is actually like a large challenge recommender like systems field, right? As you can see, it's very powerful. It drives a lot of like business revenue, drives a lot of profits for most like large tech companies. So it's quite important. Let's first understand why this happens, right? This happens exactly because like one of the reasons I mentioned earlier, it's hard to measure the thing you're truly trying to optimize for. For example, in the case of Google, they're trying to optimize for, okay, this is the information that William would really benefit from at this current moment, right? But how exactly do they measure that? The one of the best proxies is that, well, does William actually click on this thing, right? That's all they get to know. Now, let's say Neuralink is very advanced, and let's say you don't object to having everything in your brain shown to Google. Google can be more in predicting, oh, actually, like William would really benefit from this because I know more about him. So therefore, here is the better recommendation, right? But until then, they optimize for metric, which is usually something like the amount of stuff you buy in your shopping cart or how many clicks you go through if you're recommended an article, right? So one of the things you can actually do is basically consider the extremeness of your product versus the versus like it's like quality, right? So maybe you learn an embedding for the space of all the possible speeches or the possible articles. Sometimes there's like extremely left opinions. Sometimes there's extremely right wing opinions. So maybe you have some sense of that, right? And then what you can do is actually say, okay, I want you kind of like stay in the neutral zone. Or you can say, you know what, for every opinion I present to you that is a little bit on the extreme side, I want to also recommend you something on the kind of like equivalently far to the left side or far to the right side of things, right? So what you're really trying to do is kind of like keep things balanced, but this requires a lot of like forethought and a lot of like after processing. So the other thing that people will do is basically the role of content moderation, right? I'm just gonna remove everything that I don't want to touch. So right now, what's interesting is that if you tried, Bard or some of these Google products, and you ask it about a very divisive topic, for example, the topic of abortion, right? It's a very heated topic. You can't really say one side is right or wrong. It will just not say anything, right? So these are some of the ways that you can use to essentially avoid radicalizing people. But this is a huge problem because from the company's perspective, if you keep clicking on things that is being suggested, it's an indicator of success, and maybe it actually leads to success in terms of like more advertising revenue. But in the long run, this is actually causes a lot of harm for humans, right? So one solution is actually to develop better metrics for the neural networks to optimize for. Or you can develop a set of metrics. For example, what is the likelihood that this recommending is extreme or harmful or is too outdated. So those are some of the solutions. But unsolved problem. Yep, and sentiment analysis, exactly. So that is my contributions on this. One last question. I'll answer that one. So content moderation is part of the yes, exactly.
Anything else I can help with?
Okay, away Siri.
Okay.
Thanks. Oh, that actually worked. That's amazing. Anyways, so yeah, let's take the example of like continuous training, right? Let's say you train on some, toxic stuff, and then your user was like, oh no, that's super toxic. Down, thumbs down, right? What does that look like in the back end? Okay, so maybe there's a flag associated with that piece of content that says, yeah, this one is toxic, right? Let's say your neural network has a multiple objectives. One is like how many clicks people, was the clicking on this article, and the other one is like what is the probability that this article was toxic. So you want to increase the click, but you want to reduce the toxicity, right? So maybe that's a negative score or something like that. So then you give it to your neural network to do the retraining. Now, because the content has been flagged, therefore that feature has changed. Therefore, when you get enough articles that was in your training set that has been flagged as toxic, you can then put it back into the neural network and say, okay, I want you to reconsider your choices of what you're recommending to my users because these ones are not good, and I want you to understand that these ones are not good. So there you go. Okay, so there's that. Yeah, Siri needs more training, maybe. Yeah, and also I don't know what keyword I use to trigger Siri, so I'll try to avoid triggering Siri in the future. So okay, cool. So there will be a survey that gets sent out, and if you don't want to mention what's been difficult for you, I read those surveys every time, right? I'm trying to constantly improve. So if I'm doing a good job, you can say so. But you can also say, yeah, you're doing a good job, but I wish we did more of this, or I find this part really difficult. So please cover it next time, and I'll do my best, right? And if I'm doing a bad job, definitely tell me because my goal is to be useful. So yeah, cool. I am going to bounce, and I wish you a good luck with the labs and have a good rest of the day.
Thank you so much, Maddie, for this great session. Thank you for everyone for joining today. And I wish you good luck on your learning journey, getting all the badges and the labs ready. And I will post the link of the recording of this session on the event page, and also I will add it to the video playlist in YouTube that I pasted for everyone in Slack, so you can have all the videos in one place for your learning journey. Thank you, everyone, and see you next time.